In this chapter, what we're going to be discussing is going to be carbohydrates. And in this, what we have here is we have a couple of monosaccharides. And what we want to determine, so the question that is asked here is classify each of the following monosaccharides. We have two monosaccharides. Here we have xylose and tagatose. Classify each of the following monosaccharides as an aldopentose, a ketopentose, an aldohexose, or a ketohexose. So first of all, we have an aldopentose, which means it's going to be an aldehyde with 5 carbons. We can also have a ketopentose, which is going to be a ketone with 5 carbons. Or we can have an aldohexose, which is going to be an aldehyde with 6 carbons. Or we can have a ketohexose, which is going to be 6 carbons that happens to have a ketone associated with it. So let's first start out with the xylose. All right. Now, what we have here is we have a whole bunch of alcohols here, or hydroxyl groups, which would also be alcohols. Now, we look up here at this carbonyl group, and we have a carbon double bond to an oxygen, which is going to be our carbonyl group, and this is going to be bonded to a hydrogen. So if we happen to have a carbonyl group bonded to a hydrogen, we know that this is going to be an aldehyde group. So this is going to be our, sorry, my penmanship is terrible. That's going to be an aldehyde, all right? Now, if we start counting the number of carbons, here we have 1, 2, 3, 4, 5. We have 5 carbons. So this is going to be what's referred to as an aldopentose. That's going to be an aldopentose because we have an aldehyde with 5 carbons. Now we come over here to tagatose. And once again, here we have an alcohols. Here happens to be our carbonyl group. We want to look at that carbonyl group. And we have a carbonyl group that's bonded to a carbon and a carbon. So this is going to be a ketone group. If we count the number of carbons, we have 1, 2, 3, 4, 5, 6. We have 6 carbons. This is what's going to be referred to as a ketohexose. Keto meaning we have a ketone group, and a hexose meaning there's going to be 6 carbons. Okay? Now in this question, what it asks for is identify each of the following structures as either being chiral or achiral, and if it's chiral, indicate what is the chiral carbon. Now remember, chiral is where a carbon is, where a particular carbon will have a mirror image, and that mirror image will not be superimposable on itself. So for instance, you look at your hands, right? You take your left hand, you take your right hand. They are mirror images of one another, but if you try to superimpose them, they're not. The thumbs do not line up. The thumbs actually line up with the pinkies, right? And so this would be what's referred to as a chiral molecule, all right? Your feet are chiral. However, a pair of socks are not. They're mirror images, but they can stack on top of one another perfectly, all right? So a real simple test, at least for this. This is what we're going to use to determine whether they're chiral, because this is going to be a little bit hard to see the mirror images. What we're going to look at right now is that if a molecule is going to be chiral, and if that carbon, if the carbon is going to be chiral, it's going to have 4 groups. Now, not all of the carbons have to be chiral in a molecule. It only takes 1 carbon atom to be chiral for the entire molecule to be referred to as chiral. So once again, what we're going to look for in this case is we're going to look for carbons that happen to have 4 different groups, all right? So for a molecule to be chiral, the carbon atom must have 4 different groups bonded to it, and then the mirror image is not superimposable on top of the object, all right? But that's going to be very hard to see in this case. We'll get to a problem like that in a few minutes. But all we really want to determine is, are these molecules chiral or not? And to do that, we're simply going to see if each carbon has 4 different groups bonded to it, all right? So let's start with the first molecule here. Now this carbon is not going to be chiral because remember, it's got to have 4 different groups. So this carbon happens to have 3 hydrogens, and then all of this stuff is going to be referred to as a group. Okay? Now we look at this carbon, the next carbon, it's going to have 2 methyl groups bonded to it. So there's only going to be 3 different types of groups bonded to this carbon. We have 1, 2, and then all of this is going to be a group, and that would be 3. We move on to the next carbon. This carbon is going to have one group here. It's going to have another group here, but it happens to have 2 hydrogens. So this carbon is achiral or not chiral. Let's go to the last carbon now. If we look at the last carbon, this carbon happens to have one group here, 2 groups, 3 groups, and now that happens to have 4 groups. So let me circle those 4 groups for you. So this is going to be group 1 right here. This is going to be group 2, group 3, and group 4. So this carbon happens to have 4 groups bonded to it. So this carbon here is chiral. That carbon there is going to be the chiral carbon. We have a lot of C's. Sorry. So this is going to be the chiral carbon, and so thus the entire molecule is chiral. All right. Let's move on to the next molecule here. So we look, and what you want to do is you want to look at those carbons, right? So we have this carbon here, which happens to have 3 hydrogens, and in this group, so that's only 2 different groups. Now, this carbon cannot be chiral because we have a double bond here. Likewise, this carbon cannot be chiral because it has a double bond, because there's only going to be 3 things bonded to it. So this carbon only has 1, 2, 3 things bonded to it. This carbon has 1, 2, 3, so it only has 3 things. So this molecule is not chiral, or it's referred to as achiral, meaning not chiral. All right. Let's look down at this molecule here. So we look at this carbon here. Once again, you want to look at the carbons and count how many different groups are bonded to that carbon. So this carbon has 3 hydrogens. That's not 4 different groups. Okay. This carbon happens to have 2 methyl groups, so it cannot be chiral. We go to this carbon molecule. This carbon molecule happens to have 1 group, 2 groups, 3 groups, and now this is all 1 group as well too. So this carbon has 4 different groups bonded to it. So the molecule is chiral, and that carbon atom is the chiral carbon. Okay. Let's move on to the next one. We have a bromine. I'm not going to count that. So once again, we just want to look at the carbons. This carbon happens to have 2 hydrogens and a bromine. So because it has the 2 hydrogens, this carbon cannot be chiral. Likewise, this carbon cannot be chiral because it has 3 hydrogens associated with it. So if we look at this carbon, it happens to have 1 group, 2 groups, 3 groups, and 4 completely different groups. Now, if this happened to be a hydrogen, if this was a hydrogen here, this would not be a chiral molecule because it's the bromine on this methyl group that distinguishes it from a simple boring methyl group. And so this becomes a chiral molecule, and the carbon here is the chiral carbon. Okay? Once again, we're going to continue our talk on chiral carbons and chiral molecules. So this says identify the chiral carbon in each of the following. Amphetamine, all right, which is benzodrine, which is a stimulant that's used for the treatment of hyperactivity. So that's going to be the one in yellow. And then down here in pink, what we have is we have norepinephrine, which increases the blood pressure and nerve transmission. All right. I'm not a biochemist. I'm a physical chemist. Not used to looking at these larger molecules or seeing those type of compounds. Sorry about that. I'm much more comfortable with math. Anyway, what we want to do is we want to be able to identify the chiral carbon. Now what this is this is going to be a 6-membered ring. So each angle there is going to represent a carbon, and not shown here is going to be hydrogens off of each one, just 1 hydrogen. The ring around here means that we have an alternating double bond, all right? So that's not going to be the chiral carbon. Here, this is not going to be a chiral. Well, I mean, none of these carbons are going to be chiral carbons because they're only going to have 3 things bonded to them because of alternating double bonds. It's called a benzene ring. This carbon is not going to be chiral simply because it happens to have 2 hydrogens bonded to it and it doesn't have 4 different groups. So this is going to be the chiral carbon because it has 4 different groups. It has 1, 2, 3, 4 different groups bonded to it. All right. Now we go down to this one. This is norepinephrine. Once again, We have the benzene ring here with 2 alcohols coming off of it. We have a carbon with 2 hydrogens, so this is not going to be carbon or chiral carbon, but this carbon here is going to be a chiral carbon, and the molecule is going to be chiral, and it's because we have 1 group, 2 groups, 3 groups, and now all this is going to be 4 groups, and so this carbon here is going to be, oops, I can't spell tonight. This is going to be the chiral carbon. So this molecule is going to be chiral, and those happen to be the chiral molecules, the chiral carbons in these molecules. Okay, once again, we're going to continue talking about chiral molecules. This is very important to carbohydrates because you'll see about when we talk about enzymes, and even somewhat in this chapter as well too, we talk about different carbohydrates, different monosaccharides. Once you get to some polysaccharides, the difference between a starch, which is what you can eat, a type of sugar you can eat, which is found in potatoes and whatnot, is different than that of cellulose, even though chemically they're exactly the same, but the only difference is the chirality of a particular carbon. And this happens to certainly deal with a lot of medicines. Thalidomide is one of those medicines in which you have 2 molecules, different orientations. They happen to be what are called enantiomers. All right, that's what this question refers to as enantiomers. They happen to be enantiomers of one another, and thalidomide was developed in the 1960s and was given to women in Europe who were pregnant, who were struggling with morning sickness. But one of the enantiomers, or one of the orientations of thalidomide, helped with morning sickness. Another version of it, which was in another chirality or another orientation of the molecules, caused massive birth defects. All right, and so they happen to be enantiomers, and they're very, very, very difficult to separate, these enantiomers, because they have very similar chemical and physical properties. But what they differ in is how the enzymes in the body react to them. And so that's what this is. This question refers to enantiomers. Enantiomers are going to be a pair or 2 molecules, and if they're chiral, right? If they're both chiral, then they're going to be enantiomers, all right? And so once again, we want to determine whether these molecules are chiral. Remember, in this case, chiral means 4 different groups, but then the mirror images are not going to be superimposable upon themselves, all right? And so the question states, indicate whether each pair, these happen to be Fisher projections, represents enantiomers or identical molecules, all right? So here's how I think of these, okay? So we're going to work with this pair here first. I sort of look at this ampersand as a mirror, all right? So if this is going to be our mirror, right, this is going to be the object, this is going to be the image. In this case, we have this chlorine is going to be very close to the mirror, so that's going to be close to the mirror. The bromine is going to be far away from the mirror. This bromine happens to be far away from the mirror. Now, if you were to take this molecule and put it on top of it, right? So let me go a step back. This carbon has 4 different groups, 1, 2, 3, 4, 1, 2, 3, 4. So they all have 4 different groups. Now, what we want to do, though, is if you take this molecule and set it on top of this, you'd see that these alcohols would align, these methyl groups would align, but this chlorine would align with the bromine, and this bromine would align with that chlorine. And so that tells us that these are both chiral molecules, and they happen to be enantiomers of themselves. Now, let's say that this chlorine was switched with this bromine, such that the bromine was here and the chlorine was there. Well, then they would no longer be mirror images of themselves, and they would stack exactly on top of themselves, and so thus they would be identical molecules. Okay? But in this case, the way they're drawn here, they happen to be enantiomers. Let's look at this next example. Well, a sure-tale sign is that this carbon atom only has 1, 2, 3 different groups associated with it, and this carbon once again has 1, 2, 3 different groups associated with it. So this is not going to be enantiomers. This is going to be an identical molecules. So these happen to be identical molecules, okay? Come down here, once again we look at the carbon at the center. 1, 2, 3, 4 different groups. 1, 2, 3, 4 different groups. We're going to use the ampersand as a mirror once again, right? So this is going to be our mirror, all right? The hydroxyl groups are going to be close to the mirror. The hydrogen atoms are going to be far away from the mirror. So now if we take this molecule and set it on top of this molecule, the OHs are not going to align. This hydrogen and this OH are not going to align, just like your hands stacked on top of one another. So this would be an enantiomer, or they would be enantiomers. All right. Now, once again, let's look at this pair here. So we have a carbon that has 1, 2, 3, 4, has 4 different groups. This carbon has 1, 2, 3, 4, 4 different groups. These amines, once again, we're going to use the ampersand as a mirror. We can use this as the object, this is the image. Here, this amine group is going to be close to the mirror. This amine group is going to be close to the mirror. This hydrogen is far away from the mirror. This hydrogen is far away from the mirror. Looking pretty good. So if we take this group, or this molecule, lay it on top of this amine will go on top of the nitrogen, this on top of the hydrogen, this hydrogen will go on top of this amine group, and so they are not superimposable, just like your hands. So this is going to be a pair of enantiomers. All right? Okay? All right. Now, this question asks, identify the chiral carbons, if any, in each of the following compounds. All right? So we happen to have 5 compounds here, 1, 2, 3, 4, 5. Once again, if the carbon is chiral, the whole molecule is going to be chiral. All right. So what we want to do is we want to look for 4 different groups. Okay. So we're going to look at this center carbon here. This has, anytime you have the CH3, CH2, they're not going to be chiral carbons. Okay. So you want to look at something that has different groups associated with it. So if we look at this carbon here in the center, it happens to have 2 methyl groups. So we know that this is going to be a chiral or not chiral, because this carbon happens to have 2 methyl groups associated with it. Okay. Now we look at this molecule, and the carbons that stick out is this carbon sticks out because we have a carbonyl group, but that only has 1, 2, 3 groups associated with it. But if I look at this carbon, it happens to have 1, 2, 3, 4 different groups, and so this is going to be chiral. All right. Come down to this molecule, once again, it happens to have 2 methyl groups and 2 alcohol groups, shouldn't say alcoholic groups, 2 alcohol groups associated with it. So this is what's going to be referred to as a chiral. It's not chiral, okay? We look at this molecule here. This, once again, this is not going to be chiral. That's not going to be chiral. This is not going to be chiral because the H3. So if we look at this carbon here, it happens to have 2 methyl groups, so that means it's not chiral. And this carbon only has 3 groups associated with it. 1, 2, or 3 groups bonded to it. 1, 2, 3. So this is a chiral as well, because this carbon atom has 2 methyl groups, so that's 1 group, 2, 3 different groups. So it's got to have 4 different groups associated with it. Once again, we come down here. This carbon certainly sticks out. This carbon's not going to be chiral, or achiral, achiral, achiral. So the only one that has a chance of being chiral is going to be this carbon. And it happens to have 1 group, 2 groups, 3 groups, 4 groups. So this happens to have a methyl group, an ethyl group, a bromine, and a hydroxyl group associated with it. So that's 4 different groups. So this carbon here is going to be chiral, thus making the entire molecule chiral. All right. Thus ends this chapter on carbohydrates. I basically did the problems that I thought would be most difficult for students to do on their own. This chirality is a very difficult subject, but it becomes extremely important. If you happen to have any questions on this miracle, or this not a miracle, if you happen to have any questions on this problem, I know it's a miracle I got through it. If you happen to have any questions on this problem, please let me know, all right? Have a good day.